There's heat and there's cold. We are mainly going to focus on cold as a way to buffer heat. Cold, I would argue, is even more powerful than heat as a tool. And I'm not just talking about putting ice packs on sore muscles or slightly sprained limbs and ankles and things of that sort. We're going to talk about cold from the standpoint of thermal physiology. This is a literature that's rich in scientific information that goes back very deep into the last century, where physiologists and neuroscientists figured out that there are different compartments in your body that heat and cool you differently, and that you can leverage those in order to double, and as I mentioned before, even triple or quadruple your work output, both strength, repetitions, and endurance. So this is not weak sauce, as they say. This is the stuff that can really shift the needle quite a bit. And it's not just about performing well once. It's about being able to perform well and recover from that performance so that you do even better when you're not incorporating these tools. On days where, for instance, you can't access cold or an ice pack or an ice bath or things of that sort. Okay, so we're going to cover cold. We're going to talk a little bit about the physiology of cold and heat and how they work, because as you've probably heard me say before, if you can understand some mechanism, if you can just push yourself through a little bit of new knowledge into understanding a little bit of mechanism about how you work, you will be in a far better position to implement the tools in the best and most flexible ways for your needs. Everything I'm going to talk about pertains to both endurance exercise and strength and speed type exercise. So sprints, weightlifting, endurance work, and to some extent flexibility, but we're going to cover flexibility in depth, as well as another feature that's not often talked about, which is suppleness or smoothness of movement over different ranges of movement in a subsequent episode. Let's start by talking about temperature. What is temperature? How does temperature impact the body and its ability to perform, including learn new skills? So everyone probably remembers or has at least heard of the word homeostasis, right? That the body wants to remain in a particular range of temperatures, that it doesn't like to be too hot or too cold. And I want to emphasize from the outset that there are many mechanisms that are installed into us by way of our evolutionary design and our genome, meaning we were just born with this stuff ready to keep our body temperature in a particular narrow range. Heating up too much is just plain bad. It's not just bad for physical performance, it's bad for all tissue health. If your brain heats up too much, neurons start dying, and those neurons don't come back. Okay, you may have heard about neurogenesis, the ability for the brain to regenerate itself or generate new neurons in adulthood. There's very little neurogenesis, in adulthood, even anytime after puberty, really. And you don't want to lose neurons in the central nervous system. If you get too hot, that'll happen. It's called hyperthermia. You want to avoid hyperthermia. And you have many mechanisms that are built into you to avoid becoming hyperthermic. The other thing that happens when we get too warm is that we have in all of our cells what are called enzymes. You generally know if something's an enzyme because it ends in the letters ASE. Right? So lipase is an enzyme that exists to digest fats. You have proteases that are there to digest proteins, right? So anytime you see ASE, chances are it's an enzyme. Enzymes are proteins, and they have a particular structure, and their structure becomes modified when heat increases. And that's not good. You want their structure to be of a particular type. Imagine a car with 4 wheels. Let's just say the car is the enzyme. If it gets too hot, it's like 2 of the wheels fall off, and that thing can't function. So one of the reasons why the body and nature goes through so much effort to build in mechanisms to make sure that we don't become too warm is because when we get too warm, these enzymes don't function. Cells stop functioning. They stop being able to generate energy. They stop being able to digest things. You stop being able to think. And eventually, those cells start dying off entirely. So keeping temperature in a particular range is really good. You don't want to get too hot. We have much more flexibility in terms of getting cold. Now, you don't want to become hypothermic either. You can die from hypothermia just like you can die from hyperthermia. However, that you have a lot more range to be cold than you do to be too warm. Okay? And in general, the idea is to keep the body and brain in a particular range, but anytime we do anything, our body temperature can shift. So, for instance, if you were to stand next to a campfire or you were outside on a hot day, various things would happen to dump heat from your body. If you were outside on a cold day or you were to get into a cold shower or a cold lake, various things would happen to insulate heat within your body. This is all pretty straightforward and obvious, I realize. Now, what are those things? Well, there are a huge category of them. When you get into cold water, you secrete adrenaline. On a hot day, if it's really hot or in a very hot sauna or in the hot desert, you will generate what are called heat shock proteins, which will set off other sets of cascades, metabolic cascades, biological cascades. But the simplest way to think about this process is that when we get cold, we tend to vasoconstrict. Our blood vessels tend to constrict, and we tend to push energy toward the core of our body to preserve our core organs. Okay, so our periphery, our hands and our feet and our toes and our legs become colder, and our core, therefore, can maintain blood to that area, and we are insulating our core. Conversely, when we heat up, our blood vessels vasodilate. They expand a bit, and more blood flows to our periphery, and more blood can move throughout the body generally, and we will perspire. We will sweat. Water will actually get pulled out of the blood to some extent, moved up through sweat glands, and will be brought to the skin surface so that it can be. Now, it's pretty hot, but that temperature can be generated locally really fast. Now, if you're too cold, it's true, it's hard to generate muscle contractions. I got into doing some cold water swimming a little while ago, and we would joke that, you come out of the water, we do no wetsuits. I'm not recommending people do this necessarily unless you're certainly with somebody else who's skilled at doing it, which I was. And you come out and you feel like you have claws for hands. You could never text on a phone for the first few minutes. I mean, the water was very, very cold, and you can't even move your face. And so muscles will become rigid, but heating up muscles causes them to fail to be able to generate more contractions. Put simply, if you get too hot, you stop exercising. You may not even realize it, but your will to exercise further, your ability to push harder, is entirely dependent on the heat of the muscle, both locally and your whole system. So let's talk about your whole system, because I just described heat dumping and heat maintaining. I told you that increasing heat makes it hard for muscles to contract. It will stop you from being able to run further and faster. It will stop you from being able to lift more weights, more sets, more repetitions. If you can keep temperature in range, however, in a proper range, you will be able to do more work. You will be able to create greater output. You'll be able to lift more weight, more sets, more reps, and you'll be able to run further. Now, there are data that I'm going to talk about in a little bit that are absolutely striking that underscore that statement. They are data from my colleague Craig Heller's lab in the Department of Biology at Stanford. And they are data that are now being implemented. They were first implemented in a grant funded by DARPA, but now in professional sports teams. Many, if not all, the NFL teams are now using this technology, as well as military uses it. And not just for sports performance, but also firefighters, construction workers, other professions where elevated heat becomes a barrier to performance. And you can leverage this to really improve your workouts. And when I say really improve, it is striking. I'm going to give away a little hint of this now, and then I'm going to tell you a little bit more of the data later after I tell you the protocols. Proper cooling of the body, which has to be done in a very specific way, has allowed recreational athletes, so college students and typical adults, as well as professional athletes, to go from doing their usual output. In this case, what comes to mind best would be a particular professional athlete who's a member of the 49ers at the time, was able to do 40 dips on his first set, 30, 20, 20, basically did 10 sets of dips, unassisted with anything else. That's an impressive, especially since he's a really large guy. 40 dips is a respectable. These are strict, full range dips. And then by the 10th set, there's a steep drop off. Using proper cooling of particular body compartments, he was able to triple that within less than a week and maintain that performance even without the cooling approach. So it was actually a conditioning effect. All right. I'll get back to this in a little bit, but there are other fantastic leaps of effort and leaps of performance that were demonstrated, including endurance running. Before I continue any further, I just want to underscore again that overheating is terrible. There's a famous example of this. This was about 10, 15 years ago when a number of dietary supplements that included things like epinephrine, which is a stimulant. It's a beta-adrenergic stimulant. Drugs like clenbuterol, which were then banned from the Olympics, which are still out there, have been in recreational use, which were beta-adrenergic agonists. So these are drugs that sort of mimic epinephrine, adrenaline to some extent. I know I'm oversimplifying this here. They improve fat loss because of the effects on metabolism, but they heat up the body. And what happened was, this hit the press very widely, is high school football players and various professional athletes were dropping dead because they were overheating during practice or in competition. So much so that clenbuterol was banned, although every once in a while somebody gets in trouble for using this. There was an instance of this recently in professional boxing, which was attributed to bad meat that contained the clenbuterol. I don't know what the source was. I don't have any commentary about that, but it still is in use. But these drugs increase body temperature, increase fat loss, but carry a severe danger. And that's the danger of hyperthermia. In fact, I would argue, and I think in talking to some folks in various professional fighting organizations, it's very clear that a lot of the deaths that one sees in professional combat sports may have to do as much with dehydration and overheating as it does with getting hit in the head, which is also bad, but that things can compound. They can have a synergistic effect. And just a note about that and hyperthermia and its dangers as well. My first project ever in science was to evaluate the thermogenic effects of MDMA, of ecstasy. That was my senior thesis in college, actually. And so what we found was that indeed drugs that remove your understanding of how warm you are cause you to not take on the appropriate behaviors to cool yourself, right? So your vasoconstriction and your sweating, those are autonomic. Those are going to happen no matter what, unless you happen to take something that blocks that effect. However, there are a lot of things that we as humans do to prevent ourselves from overheating. And the main one is stop. When we are running in the desert or when we're running very hard and suddenly we stop, oftentimes that's because the muscles are overheating. It's a subconscious thing. We won't often think, oh, I'm really much too warm. It's just that we stop, and it's a self-preservation mechanism. Sometimes it kicks in too early. Sometimes it kicks in too late. Kicks in too late, you can die. There's an instance in the 1984 Olympics where that was the first year, I believe, that there was a women's marathon. I think that's correct. And one of the front runners or top picks for winning was heading into the stadium. And all of a sudden, it seemed as if she was lost. She was kind of wandering around, not knowing where she should go. And in fact, she was in a position to win, or at least take second place, at least take silver, got totally disoriented and did miserably in the race. And she was hyperthermic. She was running against that reflex to stop. So dumping heat is key. So how do you dump heat in order to perform longer safely? Well, in order to understand that, you have to understand that the body has three main compartments for regulating temperature. Okay, we don't just have a center and a periphery. We have three main compartments. And there's one compartment in particular that all of you, or most all of you, I have to assume, have. And if you can understand how that works, you can do tremendous things for your performance and for your recovery.